This presentation is delivered by the Stanford Center for Professional Development.
Okay, let's get started. So today's video is about juggling. This is from Dan Kodicek, and it was presented at ISRR, International Symposium of Robotic Research in '93. Video. Okay.
At the University of Michigan Robotics Laboratory, we're interested in tasks involving dynamically dexterous interaction between robots and their environments. Computers currently play chess better than all but a few of the best human experts. But no machine has yet been built that can manipulate the physical pieces with anywhere near the skill and reliability of the youngest human chess novice. Our 3-degree of freedom direct drive robot is endowed with a juggling algorithm that transforms the positions and velocities of a falling ball into desired joint positions and velocities, which the robot is forced to track by use of a non-linear inverse dynamics controller. Smooth position and velocity estimates are produced by a linear observer, which in turn receives input from a real-time stereo vision system. The one juggle task requires the machine to bat a single ball into a stable periodic trajectory passing through a user-specified apex. Adding a second ball with an independently specified apex point defines a 2-juggle task. The juggling algorithm shown here employs an urgency measure to switch the machine's interest between the reference commands corresponding to the 2 independent 1-juggles. It's worth emphasizing that there is no planning in the conventional sense taking place in this system. Rather, the robot's impact decisions are induced by its continuous motions in the effort to track a carefully distorted version of the positions and velocities of the 2 balls. Machine juggling skills in themselves seem unlikely to play a direct role in the social and economic impact of advanced robotics. However, we are convinced that the problems of controlling contacts, focusing visual attention, and coordinating in real time the constituent behaviors of such skills provides an invaluable laboratory for understanding what is hard about dynamical dexterity. Without a phase regulation control term, the balls quickly wander in phase and eventually fall simultaneously. In contrast with phase regulation again enabled, nearly simultaneously falling balls are successfully separated. In this experiment, we failed to prevent a spatial collision. We hope in the future to better understand the nature of these and other dynamical obstacles in order to control around them more effectively. Of course, there will always be situations from which the machine cannot recover.
Okay. So, who's interested in juggling? Well, those who are interested in juggling could try it next quarter in experimental robotics. In fact, a lot of the projects in experimental robotics involves dynamic skills, throwing a ball into a basket, playing ping pong or whatever. So juggling is quite challenging, actually. Well, juggling requires control, and here we are. So, this is a little bit of a concept that we are going to see over the discussions on control, and the concept is, instead of really thinking about the robot as a programmable machine where you need to find all the joint motions corresponding to your task. So you want to move to some location and you want to be able to reach that location with some orientation of your effector. Well, basically what you have to do is you have to solve this inverse kinematic problem to find the joint angles that would allow you to be in that configuration. I'm not sure if a human do that. Human usually are really poor at computation, so finding the inverse kinematics, finding all the joint angles that will put you in that final configuration, it's really difficult. So what do you think humans do? Feedback of what? So you sort of like think, I mean, try to reach for something. Try to reach for the chair in front of you. How do you do it? So you're looking at your hand, you look at the chair, and you have this visual feedback servoing. So it's sort of like your hand is attracted by a force pulling you toward that goal position you described. And this is the concept you see here. It's sort of like potential energy, where the minimum of this potential energy is located at the goal position. And that is going to create a force pulling your hand toward the goal. Your hand is going to just move toward this goal without a priori imagining or knowing where your final configuration is going to be. The final configuration is going to emerge from your motion. We will come to this later. But this kind of idea is really what we call task-oriented or operational space control. The idea of really doing the control not through this inverse kinematic and programming the robot. Well, there is another method, and most robots today are controlled through inverse kinematics. That is, we control the joint motions. So you first decide where you're going to position your hand. So you need to find this configuration, which means all what you know is the position and orientation of the hand. You don't know yet this. So you need to do the inverse kinematic. You saw the inverse kinematic for 6 degrees of freedom. How about inverse kinematic for this? I'm not sure. But anyway, you might maybe use a mannequin, and you just position it, and you decide, well, this is a good configuration, and you start from here, and now you servo your joint angles to move to that final configuration. Well, it doesn't really work very well with humanoid robotics, and in fact, a lot of humanoid robotics today are suffering from this problem, the fact that we are still controlling robots using inverse kinematics. However, for industrial robots, well, with few number of degrees of freedom, or if you have a repeatable task, you're repeating the same motion over and over, basically you recorded the motion, and what is left is how to track that motion. So today we're going to discuss the basics of control, and we're going to really start slowly with just something like we saw on the video, just natural systems, like you're dropping a ball, or you are looking at a pendulum moving, and you are trying to understand just the relationship between the potential energy applied to the system and the kinetic energy resulting from its motion. And then we will analyze how this behavior would allow us to create something like PD control, proportional derivative control. Well, in nature we don't have too much of integral action, but we will be able also to add integral action if the error is large. And then we will apply this to controlling robots in joint space. So we can control this robot to follow a trajectory that is given in joint space. And then we will discuss how we can apply control techniques directly to the task in the way we do it human. That is, by directly applying a force, not through the inverse kinematic or at the joints, but directly to controlling the end effector motion, velocity, and acceleration. So at the end, we will see that motion control is not really the only thing we need to do when we have a robot. You really need to interact with the environment. And in order to interact with the environment, you need to control the contact forces. So if you are sliding over a surface, you are moving, and at the same time you are applying a force of contact. And that is going to be a critical technique in order to interact with the world, affect objects, assemble, move, and cooperate with different robots. So a manipulator like this one can be controlled directly through its joint motion by simply imagining that you have some sort of like springs at the joints. And if you put just springs, then the mechanism is going to oscillate if you disturb it. So what do we need to add? I'm just talking about passive mechanism. So we put a spring and now it's going to hold itself at some configuration. And if you disturb it, it will oscillate. So what do we do to make it more like asymptotically stable? Put some damper. So if you place a spring and a damper at each of the joint, you will basically go to that resting point of all the springs, and that will allow you to be at that configuration, right? So to control the robot in joint space, just imagine that the resting point of the spring is changing. So little by little you're here, and then you're moving it there and there and there, and then you can control the joint motions. So this is typically the approach that we will have in joint space control, except the fact that we are not really dealing with the coupling, with the inertial forces created. And we will see a little bit more about this. We will see why this could work. I mean, it's not obvious that it's going to work. With passive devices, if you put just spring and damper, the system is passive and is going to somehow rest at some configuration. There will be deflection due to, even at a steady state, like if you let it rest. What other forces will disturb the position? So the springs will go to their rest position, but they will deviate a little bit because the gravity. So the gravity will create little disturbance. You need to compensate for the gravity, to account for the gravity. You need also, during motion, to account for these acceleration you are generating, and that are scaled by the inertias and the masses, so they produce coupling, as well as centrifugal Coriolis forces. So the equation of dynamics is here, and now we need to account for that. But simply the concept of the control is just a spring damper system, and the behavior is going to be very close to a mass spring damper, except the fact you have coupling. So if we start over and we want to control the robot directly with respect to the task, so we want to move this in the effector to some location, what can you do? Still using some passive springs and damper. I'm going to give you one big spring and a damper, and you just need to place it somewhere. Yes?
Perhaps specify a GPS position? Maybe it could go there. I don't know.
Yeah, the GPS position is good. It will give us where the robot is, and we know where the robot is going, so we know the error between the two. But I'm asking, what is the concept in terms of moving, implementing a controller that will work with the task instead of working with the joints? So I don't want to use this. If I place all the springs at the joints, I need to know the joint displacement. I need inverse kinematics. If I want to control the hand, yeah, so exactly. Just pull it, right? Just put the spring there. Anyway, I gave you only one spring, so you have to just place it somewhere. All right, so, okay, what is going to happen here is you are going to pull the end effector to that location, to the resting position, and it will do this, and everything will fall. You don't know where it's going to be, but it will fall. And we will see that the concept is as simply as this. Well, in 6 dimension, x, y. So the spring is like 6-dimensional spring. Okay? All right. So this is basically the concept of task-oriented control. I mean, you can think about the spring as passive spring or some attractive potential energy that you are creating at the end effector with a gradient that is pushing you towards the goal. And that gradient is actually here coming from the spring. The spring has a potential energy when it's disturbed, and when you go to rest, you reach the minimum of that energy, and essentially you're applying the gradient of the potential energy. Okay, so in just space, this is what is happening. As I said, we have an inverse kinematic problem. We have a task that is described in terms of x, y, z, the orientation of the end effector, alpha, beta, gamma, whatever representation you have. You need to compute the desired joint motions, and then you have those desired motion 1, desired motion 2, etc. And you look where you are, so you measure from encoders your Q1, Q2, Qn. You form a small error between where you want to go and where you are. And then you are reducing this error by control, independent controllers most of the time, sent to each of the joints. So you have servo controller at each of the joints, taking the joint from some value of theta to another value of theta. The problem is you have this inverse kinematic all the time in the system. Another approach that came about as early as 69, 70, 71, and there is a paper by Dan Whitney in 72 describing resolved motion rate control. So rate means we're looking at the derivative at the velocity, and the idea is to, instead of doing the inverse kinematic using the forward kinematic and taking its inverse, the idea is to find a small displacement, delta theta or delta q, that correspond to your desired displacement, delta x. So what do you think we have at our in our menu as models that could help there? So we would like to find a relationship between delta x, small displacement. So I'm at x. I would like to move little bit, delta x. What would be the delta q? So what model we should use? And you don't say it. Someone else. Yes, the Jacobian. Actually, the inverse of the Jacobian. So here is the Jacobian. It relates precisely delta x to delta theta. Right? If you take the inverse, you have to make sure you're not at a singularity, otherwise you have to do special treatment of the configuration. If you're outside of the singularity, you will, and if you have 6 degrees of freedom, regular case, rectangular matrix, then you can take the inverse. Otherwise, you have to resort to generalized inverses or pseudo inverses. So you compute a delta theta. So for a small delta x, now you have your delta theta. Knowing your theta, knowing where you are, the next configuration you want to go to is what? theta plus delta theta. So you start from your current position x, you compute the error, that is the x desired minus your current position, and then you compute your delta theta and you add it to theta. So you keep controlling the robot to this theta plus, which is where you were plus the small displacement. And this is a vector. So here is the model. Now the Jacobian inverse is inside your servo control loop. And you need to compute the forward kinematics, which is easier to compute, especially for you now, right? Very easy, forward kinematics. So forward kinematics include the Jacobian. You just have to invert the Jacobian. And for a small robot, you can get it almost in analytical form. So basically, you compute a delta Q and you distribute it to all the joints. And you have controllers for each of the joint to move and form this error in delta Q and you move. So now you're continuously moving. Well, this has a lot of problems in terms of the conditioning of the Jacobian, the fact that the Jacobian has this strange thing about its metric, because the space where you are measuring delta x involves linear motion and angular motion. So linear motion is measured in displacement in centimeters or meters or inches, but it has also rotational motion measured in degrees or radians, and it all included in the Jacobian. So the metric of the Jacobian is not homogeneous, and that creates problems. Also, you have the singularities, you have the redundancy, you have all of that, in addition to the fact that you have dynamics. So this works usually most of the time, but it works best if you use it to find the trajectory you want to execute. In industrial robots, often you want a repeatable trajectory, and this doesn't repeat. You will drift. So if you do this in simulation, you will be able to find a trajectory. So resolve the inverse kinematic this way, and then come up with a trajectory that you can execute. Okay. Well, let's see how we're going to control the robot anyway. We get joint angles. We are following directly the trajectory. Whatever we do, we need to control the robot. We need to create a motor torque that is proportional somehow to the error, so we drive the joints to move toward the goal. So how does it work? By the way, how many of you have had some control classes? Okay, that's what I thought. So we'll start assuming you know nothing. Forget everything now, right? Okay, so what is the simplest system we can consider? Well, I think a mass spring system would be the simplest you can imagine, right? So you have a mass resting on a surface with zero friction, nothing, it's sliding, and you have a spring. You pull it. What's going to happen? That you can imagine, I'm sure, everyone. What's going to happen? From rest, you pull it a little bit and let it go. It will oscillate. So we are really interested in understanding this oscillation and how the oscillation is affected by, and by what is affected. So this problem could be resolved and looked at through this same equation we use to find the dynamics. We look at this mass and we find its kinetic energy, and we look at the system, it has some potential energy. Where is the potential energy? It is, I'm sorry? I cannot hear, I'm sorry.
Sorry. The spring?
The spring, yeah. I'm sorry, I didn't hear you. The spring. Right. So when you're at rest, the potential energy is equal to 0. I mean, if you let it rest alone, you're not intervening, the potential energy is equal to 0, and the kinetic energy is equal to 0. The velocity is 0. The kinetic energy is 1/2 mv squared. So if we disturb it and hold it, what happens to the kinetic energy? Still 0. Potential energy. Going to be positive, it will increase. Now, if we let go, the potential energy starts to decrease, and that energy is transferred to the kinetic energy. And then it keep decreasing. We come to the minimum of the potential energy. We will have the maximum kinetic energy. And now the kinetic energy, the velocity start to reduce, the kinetic energy reduce, and we start building potential energy. And essentially this oscillation is a transfer between K and V. So this is K, and we can write this equation. So if you write this equation using K that we saw here, you take the derivative with respect to x dot, it gives you what? mx dot. The derivative of K with respect to x is 0. So you get the time derivative of that quantity, mx double dot equal F. And the potential energy of the spring is 1/2 kx squared. So that gives you the gradient. When you take the derivative with respect to x, you get minus kx. Okay? So the Lagrange equation is a Newton equation. In this case, mass acceleration equal force, and the force is minus kx. It's a conservative force. So you are transferring energy between minus kx and the kinetic energy, which is building velocity and acceleration. So, for some reason it's written twice. I don't know what happened, why it's written twice, but now I move this minus kx to the left-hand side of the equation, and we have mass acceleration plus kx equal to 0. So there is no external forces. This kx is the gradient of a potential energy v, and this is the acceleration of your mass. Now, let's take a look at the response of this system. So, I'm not sure if you can see it. You see this red potential energy over there? This is the potential energy of the spring. And let's imagine this green dot that is this point mass we are going to drop. So if we drop this point mass, it's going to fall and it will oscillate, right? There is no friction. It will keep oscillating forever. So this is time, and we are looking at the frequency of crossing this axis. That is, we're going from one side of x, we're going to the negative side, and there is a frequency of crossing. So my question to you is, in relation to these two parameters, k and m, what is the effect of m on the frequency? So if your mass is heavier and heavier, what is going to happen to this frequency? And if your K is smaller and smaller, what is going to happen to this frequency? So if K is very big, what would happen? If K is 0, what is going to happen? K is 0, nothing would happen, right? K is larger, the oscillation frequency. So frequency increases with K and decreases with the mass. There is this quantity that we call the natural frequency of the system, and this is the square root of K divided by M. Anyone knows why, I mean, where this omega is coming from? Do you see it from this top equation? Somewhere. Yeah. So basically, yeah.
This A multiplies sine omega and t, and then.
Very good. You integrate the equation and analyze its response. If you don't trust this result, let's see how we can resolve and integrate this equation. So if we divide by m, we get the acceleration plus k divided by mx. Now if you integrate this equation, you get the square root of this coefficient of x that will appear. And we usually rewrite this equation on the top, we rewrite it as omega square x. So the k divided by m is really the square of your natural frequency. And if you write this equation and do the integration of this equation, you get a sinusoidal response where omega appears as the frequency of your sinusoidal motion. So in fact, x that comes from the integration of this equation is some constant cosine omega t plus phi. So what is phi and c depends of what? I heard initial conditions, right? So from the initial conditions of position and velocity, you can determine c and phi, and this is your response. And you can see that this omega is strictly the square root of k divided by m. Well, if you understand this, we need just one more step, and then you understand PD control. It's very simple. PD control actually is imitating the natural system to recreate a spring. This k will become your stiffness. K is the stiffness, and m is the mass. K will become your proportional gain, and in a few minutes we will see another k that involves the damping that also come into the equation, but not of conservative system, of dissipative system that dissipate energy because of friction. And then we will have the complete equation. So if we are looking at only conservative system without any damping, this is the response. Okay? So in fact, if we just add a little bit of friction underneath the mass as it's moving, there will be some dissipation of energy, and this dissipation would be a force opposing what? Opposing the motion, opposing the velocity. So it's sort of minus some coefficient time x dot. And that friction if we add it to the system, we have to add it on the right hand of the equation. So the Lagrange equation is capturing the natural system on the left side. On the right side, we are putting a natural force, which is friction, but we cannot put it in this left side of the equation because this force is not conservative. It is not a potential energy force. It cannot be integrated in V. So it appears on the right hand of the equation, an external friction force applied by the environment on the object. And if we assume that this force is simply proportional to the velocity, it could be nonlinear. Friction can be nonlinear. You can have column friction. You can have stiction, all kind of. If you add this force to the previous equation that we had, it appears here. This is a second order equation, general form of the equation. My system is not anymore conservative because if you oscillate now, you're going to lose energy, and little by little you lose energy and then you stop. So the mass acceleration plus bx dot plus kx is the general form of a linear system of the second order. And if we take the system and analyze it, so what we do, we divide by the mass. Do you see omega squared now? So we have omega squared, and it's, thank you very much, finished, so I can continue. Now, what we are going to do with B divided by M? Well, when we integrate those equations, this term is going to appear in some form. So what we would like to do is to see how B is affecting this damping. So for instance, if you put a large B, very, very large B, and you start falling, you're falling, you're falling. Well, if B is very large, are you going to cross? You will just asymptotically reach that goal position without crossing. So you have sort of an over-damped system. If B is very small, you're going to oscillate, and eventually you will lose the energy and you will converge towards the minimum of the energy. So here is an oscillatory damped system. With higher values of B divided by M, we have an over-damped system. And as we move from here to here, there is a special value at which we just go and reach the x-axis. And this value is called the critically damped system. And remember this, we're going to use it a lot, because we try to imitate this behavior when we control any of the systems. We will try to make it critically damped system. So we need to know for which value B divided by M reaches this value, this state. And the value of B divided by M is simply 2 omega n. So when B divided by M is equal to omega n, omega is square root of K divided by M, well, then we have a critically damped system. And this comes just simply from the integration of the equation, this condition. So now you can compute B. B, the critically damped B, is equal to what? Come on, 2 omega n times M. All right. So if you know your mass, if you know your K, then you can compute your B to be a gain for your control system. Here B is the natural damping of the environment. So the system is passive. So let's take this 2 omega n and try to make it explicit in that first equation. So I'm going to take this equation and I'm going to rewrite it as a function of omega and as a function of this critically damped system. So to do that, we take b divided by m, which is the value that we have right now, and compare it to the value that will give me critically damped behavior. Okay? So b divided by m is compared to this critically damped b divided by m. So this is a sort of ratio, right? It's a damping ratio. And, well, I need to replace b divided by m by something that make 2 omega n appear, so I need to divide by this and multiply by this. You agree? So on the left, I have this ratio, and we call this the natural damping ratio. And we use this symbol to represent it. What do you call this symbol? Psi? So we use psi. Psi represent the natural damping ratio. It's b divided by m divided by 2 omega n. So for which value the natural damping ratio gives me critically damped system? Okay, for 1. When zeta n is equal to 1, it means that b is simply twice the square root of km. And for this value, I will be able to have a critically damped system. Okay, so far so good? Not too confused? So we introduced two notions. We introduced the natural frequency, square root of k divided by m, and we introduced the natural damping ratio, this b divided by 2 square root of km. And now we can analyze our system and write it in this form. So the acceleration, it was m time acceleration. We divided by m, and we can rewrite the equation in this way. We can rewrite it acceleration plus 2 zeta omega velocity plus omega square velocity of x is equal to 0. Now, the time response of the system requires us to integrate this equation, and if we integrate this equation, we will have this response. Because of the damping, your sinusoidal, the amplitude of the sinusoidal is reduced as you move. There is a decrease, and this decrease is exponential. And this decrease depends on zeta and omega. You have the sinusoidal motion, which is function of your natural frequency, omega, but it's also function of your damping ratio. You can see when zeta is equal to 1, this will become 0, the cosine of 0. And if it's greater, then there is no cosine, because you will have only the exponential. So here is the response. So you have this exponential, and you have the frequency that is now function of omega n square root of 1 minus zeta n, zeta square. That is, the period is 2 pi omega n square root of 1 minus zeta n square. So it's not omega n anymore. Omega n was the natural frequency, but this thing that appears there is sort of a natural frequency that is affected by the damping. So we call it omega, the damped natural frequency. So it was omega, the natural frequency, and now it is damped. All right, I think this is the last definition you need to remember. And with this, we can do almost everything except the nonlinearities we have to deal with a little later. But omega, when you have damping, is really omega n, the natural frequency that appears in your spring, scaled by square root of 1 minus zeta, which comes, zeta square, which comes from your damping B divided by the mass and the spring or the gain of your system. Okay? All right, so these are characteristics of a second order system, and what we need to do is to just inspire our controller by this, and then we will be able to recreate that behavior simply by selecting what, by the way? So if you start with the mass and now you want to create a system like this, what do you need to select? You need to select the spring, which is K, the stiffness of the spring, and you need to select B. So by selecting B and K, you can create this second order behavior on a mass. So if you have one joint with some inertia, to create a behavior like this, a closed loop behavior of second order with some natural frequency, some damping ratio, and some damped natural frequency, you should be able just to select B and K and find your system. Okay? So really the control of a system is going to be almost the same. We are going to pick omega, we are going to pick zeta, which determine K and B. And then you will be able to control the closed loop. Yes?
What happens when B is a function of the configuration of the manipulator?
When V, I'm sorry.
When B is a function of the configuration, does that affect, how do you handle that?
Right. Well, B could be, actually the most general form of B is function of X and X dot, and even higher order. And then what you get is you do not get a linear system, you get a nonlinear system. So there will be additional disturbances on the system, and you need to do two things. Either to model your friction and then try to compensate for that. And that's what we're going to do for centrifugal forces. That's what we're going to do for the fact that the mass is configuration dependent. But once you model it, you can integrate the model in your control, and you can compensate for those nonlinearities. Then at the end, after compensation, you come to this form, a linearized form. So what we're going to do actually later is to go and compensate for the gravity, compensate for centrifugal Coriolis forces, compensate for nonlinearities like friction, and then reach a level where we have simply a decoupled system with M or N masses that we can control using this. Now, compensating for friction is very dangerous. It's not easy. You cannot just go and do some estimate and compensate for the friction. You can compensate for the friction, and well, we can try compensate for the friction if you want. I'll show you how dangerous it is. Okay, here is a robot. What is the name of this robot? The Puma. Okay, let's move it. It's moving. Well, it has some friction. What this is? This friction it has. You see, I'm moving it, and well, it has friction because it has natural friction. But if I remove this friction, okay, now I remove the friction. Look what's going to happen. I'm going to apply a small force. Are you all attached? We're going to move. All right, we saved it. So you can see if you compensate with for the friction, you start to have you will have quickly oscillations, and you will have instabilities. So let's say the robot is controlled now with those springs. You have 400 these are the value of the springs, and you have some value for the B's basically in here, 40. This is joint 3. So if we change this to be like 40, you see I'm pulling now, it is little bit moving. You can see joint 3. If I pull on joint 2, it is stiffer. Joint 3 is responding. I mean, if we can reduce this gain to make it 4 is good. No, that's too much. Let's make it 4. Now it's easier to move. But you see the damping? It's still like over damped. When you move it, it is not responding. So let's make this very small. Now there is little bit of motion. If we make this 0, so now if we start putting negative damping to compensate for the natural friction, we're going to go unstable. So this is a small amount. Okay, how about -9? And let's put a little bit higher again here. Okay, and obviously you're going to go unstable. The real time is not real, that's why it is a little bit weird, but it is so don't try this. No negative damping. Works. Damping, positive damping is very good. Okay. All right, so remember this omega, is it bigger or smaller? Than omega n. So you get your omega n from square root of k divided by m, and now your omega after damping is smaller. Good. Okay. All right, don't look now at notes, please. We're not hiding, you have the answers, but think about this. What is your damped natural frequency? We just saw the expression. So don't look at your notes. Okay, try to compute it. So how do you compute your damped natural frequency? You need to compute the undamped natural frequency. The natural frequency is what? 8 divided by 2 square root is 2. Your damping ratio is what? B divided by square root of kilometers, km. So km is 16, square root is 4, 2 is 8. Oh, come on, I'm not going to do it. Okay, so this is your omega, you're right. This is your zeta is, it's easy to remember, B divided by 2 kilometers square. Kilometers square, okay? Remember that? And your omega is 1.6. So you reduce it from 2 to 1.6. All right. So we have another video segment next time, but we will skip it now. So let me. All right. We have a little bit more time, so I'm going to go over 1 degree of freedom that we are going to control exactly as we did with a passive system. So 1 degree of freedom robot, we're going to assume that the robot has just an inertia or maybe a mass, so it's sliding. Maybe mass is better. If we take a prismatic joint, so a prismatic joint is going to involve just the mass of the moving link. And we're going to move it with a force, and we are going to create this force as a spring. And now we want to move to some location, so that would be the resting position of the spring. And then we can recreate exactly the same behavior on the robot. So here is the one link robot. It's just simply a mass. Probably this is the simplest robot you can imagine. It is a mass moving under this force of the motor. So the motor is going to apply a torque translated into a force F. And you want to move it from its current position to X desired. Okay? Simple problem. So we have mass acceleration equal force. So now your force is your motor force. And your task is to create a force that will let you move this prismatic joint from its current position to the goal position desired. So the same thing as a spring, what we're going to do is we are going to create this spring or potential energy whose minimum is at X desired. So the potential energy that you're creating is positive everywhere except at XD is equal to 0. So it's 0 at your desired position. And it means that you could have something like a quadratic potential energy with some gain Kp, which produces a gradient that is equal to what? What would be the gradient of this potential energy? F should be what? So you take partial derivative with respect to x. And that would be k times x minus x desired. So your system is simply mass acceleration plus kp x minus x desired. Okay? So here we have the 0 of the spring moving, changing with your desired position. That's the only difference. That's it. And that doesn't change anything. That just changes the 0. So instead of talking about stiffness, we are going to talk about the gain that you are using for your error in position. So we call it position gain. And immediately we can go to the equation and analyze what happens if I apply this controller and whether this controller is going to be stable or not. We can go and do this analysis on your on the equation of Lagrange on that system, and we analyze what happens when we apply a force that is the gradient of this potential energy. So our potential energy is this. We took the gradient of the potential energy and we applied it. Now, going from this page to this page, it's interesting because here I was looking at just 1 degree of freedom. But if we go here, we can show that whatever the number of degrees of freedom, if we apply a controller like this, essentially, so this could be 6 degrees